All right. So in this video, we're going to try to basically start picking apart the LC4 content more. What that means in practice right now is that we're going to take a look at getting a frame from our file and then getting frame blocks from that frame. So we might actually jump into the LZ4 code and take a look at what that means at the moment. But let's view this from this perspective here first and see if we can sort of make some progress. I want to just sort of, yeah, I'm going to try something here. Let's say frames. Like this, frame blocks actually, we can say. Make dynamic LC4 frame block. This is 0, 0. So by the way, I should say, when you make dynamic array like this, here, of course, is the type. We're making a dynamic array of frame blocks like this, right? And then here comes the initial size and the capacity of this, right? Which means if you know you're going to have 10, you can just say 10 here, for example, right? Then we won't actually allocate anything new until later, right? Until we reach the size where we have no longer allocated enough, for example, right? So this actually allows us to kind of reserve space if we want to. So now we have a dynamic array of frame blocks. And what I kind of want to do here, we have this load file, right? This gives us a frame descriptor. But what load file actually does internally here is that this we have this rest argument here, which is actually rest data from whatever file we read. So what I think we're going to do right now is we're going to try to kind of use that data instead. So here I'm going to say fd is a frame descriptor, and the rest here is a slice of bytes. Let's say, I don't want to call it rest actually, because we already have rest here, but it's also not quite accurate, right? Let's just say data like this, remaining data. And so here, now of course we have to modify some of our returns here, right? Like this, fd, we can no longer actually say frame descriptor. We want to return this, and that should be fine for load file. Now, of course, load file kind of doesn't work anymore like this, right? What we actually want to do now is we want to say, let's say remaining data. And this is not super descriptive, but I kind of want to do this just for now. And remaining data like this. Remaining data. Right, declared but not used. Let's kind of leave that for now. Nothing should really change now. What we could do here is we could actually say, we could put some information somewhere with some text, right? So for example, we could say I'm GUI text here, remaining bytes in file, unprocessed bytes in file, %b, len remaining data, right? Now this will give us basically some sense of what is actually happening there. We can see that this is 0 from the beginning, right? And so for example, if we said test data, plain now we can see that there are 468 bytes that we haven't processed yet because we have read only the header. We have read only the frame descriptor from this file, right? So now there are 468 bytes that are yet to be processed, and we can actually call more. We can call more functions on those, right? So what we could do here now is kind of start reading frames. The rest of the frame, so to speak. All right, so let's look at some functions we have for doing that. We're gonna, question is exactly where we're doing that. We could actually say, you know, maybe this is a button. I'm gonna just sort of say, yeah, if I'm GUI button, load more. Let's say load more. I mean, for the time being, this doesn't necessarily really matter so much, right? So what we're gonna do here now, we have the frame descriptor, right? We have the rest of the data. We can check here LZ4, right? What can we actually do now, right? And indeed, we could call frame next here to get the next frame, but that's not quite what we want to do. We actually have already a kind of a frame, right? We found a descriptor at this point. So what we actually want now is rather, let's see. We have a lot of functions here, of course. What we actually want here is maybe this frame block read. Yes. This should give us a frame block and so on. And here I actually want to say current frame block. Yeah. Elsa, do you want to go down or not? So current frame block here is going to be this. Frame block read obviously takes our remaining data, right? And here we actually want to say this, and we need to determine if we have checksums in this. So we're going to use our frame descriptor for this. Has block checksum, right? That's the second argument to this. This also returns our remaining bytes. So here we can actually say remaining bytes like this, right? And then frame block read error. And of course, here I actually have to say frame block read error is a like this. And that's because, of course, we're using an equals here, right? And equals means we're not binding any new variables and so on. So I have to introduce that one here. Not a big deal. If that's something, we actually want to log an error probably just for, you know, so we can see this in the console at the moment. Now, current frame block does not, yeah, okay, it does actually. Remaining bytes, undeclared name, remaining, what did I call this? Remaining data. Yes, I did, okay. And that's fine. Let's try this right now, right? Because now we should be able to kind of click load more to, actually I want to show the current frame block actually. So I think we're gonna do that. We're gonna do that below here. We should show all of the frame blocks actually. Now that we have a frame block, we can actually say down here, append frame blocks, current frame block. And then we can say, perhaps down here, we can do a for. So for block in frame blocks. Here I want to just say, for the time being, let's just do this, right? Elsa, what do we want to do here? Elsa, help me with the code instead of what you're doing now. This is not going to be great because we have data in these blocks. Actually, let's show this right now. I think that's fine still. This is going to be a C string. So we want to can we cast this? Not entirely sure. We'll see. Frame blocks, where are you? Did I not make, I commented us out, okay. Now we're down to one error, which is this, okay. We can't cast this, of course. Can I transmute it? We'll see. Yeah, of course, I mean, let's see here. What did I do last time with this? Let's just try that. For the time being, this is not such a big deal regardless. And let's see here. Now I'm loading a file, our trusty test data, and so on. Load more. Now we have 8 bytes more to load. I'm not seeing anything. Oh, now that's interesting. Must call end child and not end. Okay, so we have ended up doing something odd here. Right, begin child. We're using begin child here. So where are we ending up with a begin that we don't have an end for? That is really key here, right? So actually, this is interesting because where is this happening? Within end child, must call end child. We have an end child for this here. Begin child, we really only have one call to this, right? So I suspect it's here that this is actually happening. And that's interesting, right? Suspect something might be a little bit off with that. So let's load the file again here. So this is interesting, right? This is very interesting. Maybe if I move this out here, I suspect I'm sort of calling something in the wrong place, of course, right? There's something going on there. So what we're gonna do here is we're gonna try to move some of that around. You can see that it's actually happening when I scroll down, right? Because now you can see here there's a scroll bar, and once I scroll down so that something is no longer visible, okay, now we can see that this now is fine. Interesting, right? So here we have a frame block. And so let's kind of go through this. This is a very small file, so the data block here is actually not that large, right? We can see here, first of all, one of the most important things to kind of look out for is this compressed, right? We can see here that this block is compressed, right? If it wasn't, we would just we would take the content in this block and just put it in our output, right? If that was the case, if it was false here, right? We also have a checksum. This is for when we have a block, we want to determine, do we have the correct block? Otherwise, of course, you shouldn't start decompressing anything from it because it's wrong, right? So we also have a size. This is the actual size of this this slice here, right? So data here is actually the content that we will be processing in order to generate decompression, basically. And so this is what we want to move through in order to, determine what goes in our output. Because this frame block here, right, will be part of basically, this is the compressed version, right? We take this and we basically expand it. Opa. There you go, Elsa. So we take this and then we expand this to the output that we want. Hang on, I just have to let out my cat. Hi there. Hi there, son. There you go. And so we take this block of data, right? This will expand. In this particular case, it will expand to about 3,500 bytes, which is quite the compression. It's because this file is basically repeating a lot of things over and over. So we have this data. What we actually want to do is we want to move through this data here, right, step by step, and pull out sequences, right? And those sequences are basically made out of several things, right? A few. Let's take a look briefly at what this actually looks like. So here's a data block, right? This is actually what we're looking at. These data blocks are in the frame, right? That's a frame block, and is what I'm calling it, right? And so we have a size. We have a checksum optionally if our file has checksums for blocks. Then we have the data. The data was what we saw just here, right? If the size actually has the upper bit set in these 4 bytes, so this 4 bytes little endian, right? Then it means that this is uncompressed, right? That's what we saw before. So we're doing this analysis while we're reading these, right? If it's not set, it's compressed, right? And this is obviously the ideal situation is we do have compressed data, right? Because all uncompressed data that we have is essentially pointless in a compression file, right? So this data here, if we go to the actual block here, this is the block format instead, right? So the previous thing was the frame format. That is the thing surrounding the blocks, right? You can have raw blocks that don't have frames, but the frames contain information that we want in order to deal with the blocks, right? So in these blocks, right, we have a few things. First, we start with a token, and the token is really 2 values in one, right? We can actually look at the code for this when we've gone through a little bit of this, we'll look at the code and maybe you'll get a better sense of this. And so the first part of the token, the 4 first bits, highest rather, right, says basically here are the amount of literal characters that I'm going to provide after this token value. And so, for example, let's say in the beginning of a file, we don't have any output yet. What we're going to have is a series of literal values that basically are there to say, I want to copy the string package LC4, into the output, right? And then what we're going to have after this is the offset after this, right? And the offset is basically a value that says go back this many bytes from what we currently have output, right? After the literal copying, by the way, I should say. And then go back this many bytes and copy match length characters, right? So the way this actually works is we have these two values representing, hey, go back this many bytes and copy this many bytes and put that in the output, right? And once we have read the offset and the match length after this, this literal amount and then literals, we basically have the entire sequence. That's an entire sequence. So basically it follows, read the amount of literals, right? Read the literals themselves according to the amount, copy that into our output, then read an offset that says go back this many steps in what we currently have output, and then read a value that says copy this many bytes into the output, right? So we basically replicate content that is already in the output into our output over and over. And that is how we decompress this. We read just an amount of sequences that exists in our data. And then once we reach certain end cases, we jump out basically. So what we're going to do now is we're going to modify the code I have a little bit in order to read these sequences one by one. Because currently what I have is not reading these one by one. I mean, they are technically speaking inside of the code, but we don't have a function that does this at the moment. So we're going to make that function. And with that, you're going to see kind of how this works. LZ4 Odin, there you go. So here, frame block read, right? This is a function that reads a frame block. You can see here that this creates a frame block here. We have block data. The block data is what we're interested in here, right? If I say data block read, well, this is actually this is actually what we want. Basically, we can repurpose this certainly. You can see here that it stores a length, and that's the length of the literals, and then the actual literals themselves, an offset and a match length here. You can note here that this does not take an allocator, and so on. So this basically expects to hold on to whatever bytes that you kind of have given it from before, right? So there's no actual allocation happening here. It's just taking data we already have access to and basically shaping it into what we need or want, right? So we can see here, there was something I omitted from some of these things, and it's going to come into play here. We have this token byte, right? You can see here that we start at 0. We have this token byte that we read. It's just 1 byte of 2 values, right? One of them is the upper 4 bits represents the length of literals, right? You can see this here. If the field value is smaller than 15, that's it. We don't really read more. And note here that 4 bits, we can only really, the max value we can have is 15. So that means if the literals are shorter than 15, we're gonna only be using those 4 bits, and that's fine, right? However, if we have 15 or more, we are actually going to read more bytes, right? The value 15 is a special case. More bytes are required to indicate the full length, right? Each additional byte then represents a value from 0 to 255, which is added to the previous value. So if we had 15 first, and then we read 45, right? Now we have a total of 60, and we read 2 bytes in order to get this value, right? And so with that, you can then add successive kind of bytes, right? So if we had a ridiculously long set of literals, we would actually end up with 15 to 55, because that's the max value of 1 byte as well, right? And then we would read more bytes and more bytes and more bytes. So whenever we see 15, or 255, we know we need to read more, basically, right? So 15 is the first step. If we have 15, we need to read more, right? If we read 255 at that point, we need to read more, right? So how this actually works out here is we read our token byte. We say here that our initial read was token byte shifted by 4, right? That gives us the actual value in the upper 4 bits, right? We say that the block length is this, right? This initial read. Here we say the last length we had, and we set the default value of 255 here. We say if the initial read is 15 and last read length is 255, that means we want to read more, step forward, and set last read length to whatever we read, and then add this to our block length, right? Then we read the amount of literals that we have in our block length. This is now our literal value here, right? And then we set that in our block. Those are now our literals. And then we move forward that amount that we just read, right? And here, there's a special case here. We can find this actually here. Once we have read, right, following token and optional length bytes are the literals themselves. We have read this now, right? Here we then go to a match copy operation. This is just a combination of offset and match length, right? That's the match copy operation. So here we are now at the stage where we read an offset value. One of the special cases that can happen in a file, an LZ4 file or LZ4 data here, is that there is no offset value, right? So we can see this if we go down here to end of block conditions, right? The last sequence contains only literals. The block ends right after the literals. There is no offset field, right? So this is a special case. And we have this here. If we are now at the quote unquote length of the data, that means we must have, you know, there's no offset, right? So we have only literals. Then we try to read our offset, and the offset is interesting because it is 2 bytes, right? So we can have a maximum of 65,535, right? So we can move that amount back in our file, in our output, right? And so here we read these values, we step forward that amount, and we make this a U16, right? Because that's actually what we have. We have an unsigned 16-bit value here, right? And this is little endian. Everything is little endian in these files. And so if we have a 0 offset, that's actually an error. So we basically return an error here, right? Otherwise, we set our offset in our block. And then here we do this kind of initial read again. And here you'll note we're using this this pattern here that pulls out the lower 4 bits, right? And that's because we are reading a match length, right? So the match length value here, we use, you can see here, for this, we use the second token field, the low 4 bits, right? This value is from 0 to 15, just like the other 4 bits, right? But a match length can only ever be 4 plus something, right? Meaning we can't actually have 0 here. So when we have 0, it means we are copying 4 bytes. So whenever we actually use this match length, whenever we have a match, it is actually whatever number exists here plus 4, right? And this follows the same rules, by the way, as our other field, right? Because we saw whenever we read 15 from the initial or 255 from any subsequent reads, we actually continue reading. So if you have a ridiculously long match, that would be 15 plus, let's say, 236 plus 4, right? And so that is how this works, right? And once we've read this, we are done with a sequence, right? And that actually represents, here we can see that we are doing the same thing as we did with our literal length, right? We're doing an initial read. We're saying if the initial read is 15 and last read length is 255, it means we need to read more. So we add to our match length, right? And then we add 4 to our match length because those are the rules, right? And then we say return this block that we read, and then return the rest of the data we have, right? And so here, what we can do now is we can use this function, data block read, in order to read inside of our frame block. So let's try that. For block in frame blocks. I'm trying to now kind of figure out how to structure this so we can have some semblance of order here. We actually kind of want to read this frame block at load time, I suspect. As it happens, we don't actually have multiple frames in any of these files, so we could kind of rely on that, to be honest. But yeah, what are we going to do? We are going to when we say load more, we're not going to read a frame block. We are actually going to just say yeah, the remaining data here. Yeah, okay. Actually, this is fine. We're not going to use remaining data here. We're not going to set that. We're not going to set that. We're going to use it here. But, and then we're not going to use frame blocks at all. Yeah, okay. So I have an idea now. We're going to try to do this instead. Frame blocks, we can actually kind of let this be what it is. Except we're going to change the type of this to be data block. And the terminology here is something I've messed up mostly, to be honest. Data block is really the actual data. This is actually a sequence. So we're going to probably rename this at some point. And now this is that. Now we can say current data block remaining data block read error LZ4 data block read remaining data, like this. No, that is not the one we want there. We want FB current frame block dot data. Yeah. Now this is not going to be correct. Current data block. Let's say that. Okay, so remaining block data. We're gonna say this actually because otherwise we're gonna have a bad time. And load more here. We're going to say that this is a maybe, and it's nil. And if current frame block is equal to nil, we're going to do this. And the remaining block data is going to be current frame block dot data. This. Let's see what this is saying now. So I should explain here. Current frame block here is a maybe. I obviously renamed it or reworked it to be that, right? And of course, that's not what you're seeing here. If I do this now, you'll see that this is a maybe of a LZ4 must be constant. I mean, nil seems pretty constant to me. But fair enough. Let's try just doing this in that case. We're gonna do this, and then we're gonna check if the size is nil. Current frame block size is, if the size is 0, that means we didn't have one, and we are now setting one. Now we don't need this question mark, and I don't need to explain it, I guess. The question mark is actually for whenever you have a union that only has one case, which is what maybe has, right? It has a nil or some value of some type. Dot question mark is going to give you the value type, effectively, right? We don't need to concern ourselves now with this. So this is now something. So here we're now saying, okay, read our frame block. From that, read a data block, which is a sequence, which we're going to rename at some point. Current data block. Read this. Yeah. Let's try this. Yeah. The worst that can happen is that it doesn't work, and we'll debug it, and it's fine. So now we're going to open a file, test data here. Now we have this here. Now we have a data block. The length is 33. The literals are here, the offset and the match length. Beautiful. If we do this now, we have two data blocks. The length is 33. No, that is not what I want though. Right. First of all, we're gonna stop outputting the actual debug version of this, right? Instead, what we're gonna do is we're gonna output something way more structured. So now, let's say we're gonna output the actual literals like this, right? And then we're gonna output the, in fact, what we can do is we can calculate the match copy operation here. Let me just sort of yeah, we can't actually do this completely. Actually, okay. No. We can do this. I believe in us. So what we're gonna do is we are going to say output is some bytes, right? We are going to, whenever we read one of these data blocks, we're going to essentially perform this operation, right? We're going to copy into our output. Hang on, we need to copy index is 0. And bear with me here. Whatever copy index we have, we're gonna start there and copy block.literals into it, right? We're outputting this here, And here we don't want to do this here at all. We want to do this when we read the block. Extract to output. So now we've copied the literals, right? Then we're gonna say match length let's see here. We're going to take the offset, copy output block. Let me just rename this actually to block. Like this. So this is our offset. No, the copy start is copy index minus block offset, right? And then copy end is going to be copy start plus match block match length, like this. There's a special case here that we actually have to look out for. I'm going to try to not do that right now, and I'm going to explain it when it happens. Here we want to copy into our copy index like this. Copy start to copy end. And now here I want to we want to actually output this as well. We want to have some text here. We can actually do %s, %s, right? Here are the literals in the block. And then we are going to say copy bytes is equal to output. And here we actually kind of want the same thing we had up here. Sure, it's basically this. Again, there's a special case we need to look out for here. Let's try this for now. Not a big deal if this fails, we'll deal with it. Opa. Valid slice indices 20 minus 14 is out of range 0, 0. Yeah, that is not supposed to happen. All right, so let's see here what the error we had was on 236. 236. We are copying minus 14, minus 20, minus 14 here, right? That's because the copy index, when we've copied, we never actually add our literals to it. And likewise, we actually have to do this here. Copy index plus equals block match length. Like this. Valid slice indices 33, 0 is out of range 0, 0. Clearly output. This 237. This is this line again. block match length. Yeah, there shouldn't be anything super interesting there. Let's see what's happening here. Let's log some of this stuff. This could be happening on the first run, in which case, yeah, of course, we're gonna not see much happening here. Actually, let's just say copy index equals this. Copy start. Copy end like this, and copy bytes like this. Now, granted, again, if this fails before we get to that point, we're not going to see anything, right? We can put this, no, we can put it there, it's fine. File open, test data, load more, crash. Slice indices 13 to 19 is out of range 0, 0. Okay, so obviously our output doesn't actually, okay, I know exactly what the error is. Once you say something, you start vocalizing it, you actually realize, yeah, absolutely, this is why. So what we're gonna do here, our frame block does not contain, our frame block does not contain any content size, right? Because the file is just not made with content size, right? What we can do here is we can, in fact, when we read our, that's not the, yeah, I'm going to go ahead and say here, I'm going to do this now just to something like this, and mem is not imported. This is when we read the actual frame. We set up this buffer here. And content size can be set here. That's why we want to do this here, so that we actually really just allocate that, right? That's our output. Let's try this now. Because previously, the reason that this was happening was our output had nothing in it. It's basically just an empty slice, right? And that is, of course, not going to work. Here we can see we're getting output, so clearly there's something here. We can see here that I'm going to also output the literals, and we can actually take a look at why we're seeing these values that we're seeing. Copy index, etc., etc., etc. Block.literals equals like this, and block.literals So here in our output now we can see our copy index is currently 39. That means we have moved 39 bytes into our output. Our copy start here was 13 to 19. That means we were going back 13 steps and then, you know, copying to 19, right? And here you can see package, LC4 frames, etc., right? These are our literals here. Right, that's the literals. You can see it stops here. And then the copy bytes are here. So I want to show you this file to kind of show you how this actually looks for real, right? So we have test data here, and we have plain 01 txt. This is the plain text version of this file, right? So here you can see package LC4 frames, test, and so on, right? And we saw that the literals actually go towards there, right? Package LC4 frames, test, test. So we stop right before this underscore, right? These are the literals we have, right? And then we actually saw that the copy bytes, right, were frame, underscore frame, right? And why is that? Well, that's the thing that comes up here, right? And how many steps did we go back in order to get that value, right? Remember, we are here, basically, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12 is a new line, right? 13, 14, 15, 16, 17, 18, 19, right? Is that what we're seeing in the output? Yeah, copy start is 13, so we're not actually showing the offset here. That's my bad. But we are copying from 13 to 19. That's 6 characters. That happens to be here, right? So we are actually copying this value here. And that of course works out, right? Because we have this as part of our literals. This is now in our output. And then we actually say, hey, copy this section here. And that works out to be this here, right? And then we're gonna move on after that, right? So that's why this looks exactly like it looks. Now, we were seeing some kind of crash. Now, the question is kind of why, right? We're gonna close this for now. Yeah, we're not seeing why that is happening. We're really only seeing that stuff quits or whatever, right? What we can try to do here, perhaps, is say in our task file, maybe we don't build for speed. None -debug, right? And here what we can actually do is also debug compression UI. Like this. I think that's basically it. And now we could conceivably actually debug this, right? Which means we could put a breakpoint somewhere and see, hey, where is this actually, failing? We're not going to try that just yet. I want to see if we can sort of, can we get anything from this just by saying, this is not a speed build anymore. Test data, plain, load more. Now this is ending, it is really ending in the same unceremonious way. I'm gonna try just build the compression UI again, but I'm gonna force this right like this, maybe. Verbose. Okay, this is now done there. Task decompression. No, we're still not seeing anything interesting there. So what we're gonna do is debug decompression UI. Like this. No process in. We're gonna let this download some debug info stuff. And then we're gonna run the program, probably put a breakpoint somewhere So if you're hearing some noise, it's our cat trying to come in, because she cannot decide. I'm gonna put a breakpoint somewhere here. We know that we get past this point, of course, we've seen the debug output and so on. So what we can do is just sort of say, you know, put a breakpoint in decompression UI Odin 246. Break decompression UI.Odin 246. Hang on. Can I not interact with this right now? I'm actually not sure. I may have to set this already. What I'm gonna do is I'm gonna copy this and I'm gonna try a little bit of a trick. We have this GDB init file that we can do, we can use. And this is a automatic file for when GDB starts. So now we quit debug decompression UI. Now we run. I have a breakpoint there, so we're gonna hope to hit this one now. We did. So now we've hit this breakpoint, and I'm gonna just sort of put this to the side. Now we can see we're on this 246. Now we could step basically forwards. We don't have any content here, so that's fine. And if we next here, we end up on log debug if, sure. Now we append, and by the way, if you're seeing this weird output here, you can always just press Ctrl L to redraw your interface. This is just GDB being, you know, a little bit funky sometimes. Now we're appending, and here we're seeing that, okay, now we're in rendering code, right? So we're gonna be jumping forward here. Presumably all of these are fine. We end our child for every block in the frame blocks right now. And that this is, of course, we've added to this now, right? And this slicing could potentially be a problem. We're outputting this, and there you go. So there, the problem resides. And of course, once we, so actually, I don't know how to go backwards actually, but I will show you what I think this actually boils down to. We're gonna quit here just for the moment. The reason, and it makes a lot of sense, this %s, it thinks we should have C strings. But of course, we know that slices of bytes are not C strings, right? They don't have a 0 byte, in fact. So we would have to say literals C string, right? We have a slice of bytes. We could conceivably, we could actually say, yeah, no, let's do strings clone to C string here. Block literals, right? Like this. We could say copy bytes C string and like this. And now we can use these here. Right? This is at least what I think it is. We are going to see. Right, these are not strings. What we can do is instead, let's see here, bytes dot something. I'm gonna go ahead and import bytes. bytes is exactly what it sounds like. It's a section of the standard library for dealing with these kinds of things. And here we can see if we find any C string things. Probably we don't, but that's fine. What we can actually do is we can say literal C string is going to be a make of, actually we could maybe say clone. Actually, I want to see if strings has anything interesting again. Potentially we could cast our slices to strings and then copy them like this. We could try that. String like this. Now we could see if this is actually the problem. And now we can see we don't crash, right? Instead, we have output here, right? And so now I do wonder though, we do not have all of the outputs. We have test colon test, and then copy bytes frame. Yeah, we should not have this here. This is not what we should have. In fact, we should have test underscore and so on. So we want to do something else here. Log debug f copy byte C string is this. I just want to log this in to see what we actually have there, so I don't, because it's easy to confuse yourself with, oh, it's the output of the data that's wrong, it's not the actual data itself, and this can be a little bit unfortunate sometimes. And indeed, does seem to be the case right now. Because of course we know that we should have underscore frame there, right? We in fact should not have this value. So the copy bytes here are wrong. Let's see, copy start, copy end. We should be seeing the same value we have elsewhere. And so our copy start is 19, and that is of course not correct. The reason for this is because we're using copy index. We're using an old copy index, you could say. Whatever copy index we had when this actually was extracted is what we actually want to use instead. So what we're going to do here is we're going to rework this a little bit. And we're going to say that we are going to store right, we have the outputs. We have actually the data blocks. We don't need copy index here. We have our len out, but no, that's not true, because our output is longer than we are currently writing into it, so that's not true. So what we're going to do is we're going to skip this here in that shape, And we are instead going to say that we have a list of rights. And I'm going to explain what I mean by this. We're going to first make a type for this. A right is a struct with literals like this and copy bytes. Let's say this, right? Let's call this a match. Doesn't matter so much what that actually is called. What matters is much more that we are now saying that we have these, right? So we are going to say that we have this rights. We're not going to make this every time. That would be murder. So we're going to make, we have a dynamic array of rights, right? And when we pull these values out, we're going to add to that array instead, right? So we can do this here, append rights, right, which is going to be literals equals block literals, and match, which is equal to copy bytes, like this. And here I'm actually going to not do this block thing at the moment. This will now become unused. We're going to fix that later. It's fine. And now for every right in rights, we're going to actually output what that was. And now this will actually be considerably simpler, I suppose. And so now we can just sort of skip those things, and we can actually say write literals here, write match, like this. Match C string is what I'm going to call this. Not that it matters so much. Like this. This is now unused, like I said. We're gonna actually, we can just remove that, not a big deal. Now we are now writing for every right that we find, and we should be seeing that we're outputting every right that we find as well. And now you can see that we're on track, right? So here we have package colon LC4 frames. These are all literals until this point. And now what might be interesting here is actually to color these differently, actually. So let's try doing that. I think that's a good idea. Because I kind of want to show, right, that this is that way. So let's try that. First, we're going to have some text, and these are the literals. Now we're splitting them up, right? We're going to have I am GUI, same line, right? And then we're going to have I am GUI text again with just a string, and then this is just our match C string again, right? This is going to give us the same kind of, roughly the same shape, I suppose, as the other one. It doesn't matter so much because we can see that this kind of works out regardless. And now we're going to try to push different colors, right? So literals can be whatever they need to be, I suppose. It doesn't matter so much, right? But here I actually want to say push color, push style color imvec for text. Let's say that we actually have this one, like this. And here, of course, we have the pop style color as we learned before. Now we can see what is actually a literal and what is a copy operation, right? And of course, we might actually fail on the next one. Opa, this is not what I wanted. Test data, load more. Oh, right. Now this is not quite what we wanted, right? This is now using the same line, and so this is has this is supposed to go down there, of course. This we actually have to fix. If I load more, what happens now? Okay, we never step forward. That's probably not what we want. Yeah, we're gonna have to fix that as well. So now this is an interesting, I thing here, right? Because I'm gonna try a hack here. And we're gonna see kind of what happens here. I'm not so sure that this is gonna make sense, but what we're gonna try is new lines, new line count is 0 for C in literals, right? The literals. If C is equal to new line of some sort, we want to add a new line count. Actually, here we don't maybe need new line count specifically. We can say I'm GUI move. Is there a move? Pause something. Set cursor pause. Of course, we could kind of move that way. Set cursor pause Y. I suppose this is, again, this is a massive hack. I don't condone this. We'll see. We'll see what happens. Yeah, this didn't work. Of course, because we have this here, right? So this is kind of interesting. Here we might actually want to simply, what I actually want here is I need one text, but I want multiple colors in that text. And I don't think that that's something we can actually kind of do very easily. Oh, by the way, there's text colors here. We don't need to use push style. I'm GUI text. We're gonna see here if we can find something interesting. Text end. What does that mean? Text unformatted EX. We have text and we have text end. That is very interesting, right? Text filter. Not so sure what that is. Text disabled. So input text multiline, but with this we can't actually, we essentially can't have any interesting formatting inside, is what I'm assuming, right? What if we also keep a cursor position here, right? So right literals here, right, is whatever position we currently have and so on. We are now adjusting in terms of stepping downwards, right? But we're not adjusting in terms of X, right? So there might be a way we can sort of say, X plus sure, it's this, right? But whenever we new line, we actually know that we reset this. So what we can do here is X plus equals 0.0, I suppose. But if it's not a new line, we need to move to the right. No. No, this doesn't work though, right? Here we can actually say x pos plus, I don't know if 10 makes sense. Maybe it does, maybe it doesn't. We can try. What we can do here before we output this colored text is we can say I am GUI set cursor exactly like this. Now this is going to be wrong. You can adjust this for it to make sense, but we're going to try this, right? It's not a nice thing necessarily. Oh, what am I doing? I didn't open a file. Test data, plain text, load more. Yeah, that's not it. Let's say 20 first of all. And then I also think that we are doing something funky. Ah, yeah. Of course, we were outputting it twice. Okay, someone's getting a little bit tired, it seems. So let's see here. Load more. Not quite. So now it seems the Y position is a little bit off. Y pos. This is not a stable way of doing stuff, doing this, by the way. We can see here that we're kind of getting closer, but of course it's not particularly reasonable. This might be this. We would also have to do this, of course, after we have output our match string, right? We would have to count essentially the content in that and so on. I'm sure that there's a better way of doing this, to be honest, that doesn't involve doing these things the way we're doing them. Wow, this is very slow to react. I kind of feel like we should have overshot this mark a long time ago. But we keep not doing that. 40 might be overshooting the mark, finally. Okay, so this is now kind of looking sensible-ish. Now we have to tackle the fact that we are not actually, we're not moving forward in this file. So data block, this remaining block data, I want to see sort of if we can I thought that we output this, but I guess I removed this, right? Yeah, probably. Let's try to see if this ever changes, right? So here we have our copy index and so on and so forth. I'm going to say that our remaining block data, I want to just output the length of that, like this, right? This way we'll see, does this actually change over time, right? Because if it doesn't, clearly we're not moving forward in the stream. Otherwise, it is some other issue. So load more. Remaining data is for 415. When I click load more, we have 415. So clearly we are not moving forward. This means here that remaining block data is never being set. Right, because I am in fact setting a new value here instead. Let's try this. Data block read error is of course like this. Current data block. Let's rename that to block. That way we can have the other code remain as it is. We may have to find a new way to output all of this stuff, by the way. Right, so here you can see the next data block, right? And if we look at the file, we can clearly see why this is the case, right? So, oh, hang on. It's because I can't see the UI at the moment. I was wondering why, hang on, why am I? So here, right? So the first data block, we can see goes forward, the literals go forward to here, right? Then we do a copy operation that copies underscore frame, right? And then we start on literals again, which is underscore next. That's how we get this section here. Then there's a new line, right? We go 0. The literals go up until including F here. And then we can see that rame can be copied from previous positions, right? Rame here, right? We all have already seen this. That's why this is a copy operation. This is not part of literals, right? So if I now step forward even more, we can see literals go forward quite a bit here. And here we're not seeing a copy operation. I'm not entirely sure why that is. It's very odd that that would be the case, to be honest. I'm gonna see if there's some output here that we can see. Underscore descriptor. These are our literals. And the copy bytes are block. I don't know why this was not colored. Probably something I've messed up, of course. So we can see here that the copy bytes here were block, right? And if we go to our output or our plain text file, we can of course see here that we will have underscore descriptor up until here. And then, no, hang on. Ah, right. No. It is true here that we have underscore descriptor, then we have block independence equals false, and then has underscore. And now the compressor sees that we can copy block from here, right? And so it inserts a copy operation for block. And that's why. The reason probably that we're not seeing this is maybe on some level we're kind of running out of space here or something, or I am actually writing too far to the right probably. That's probably what's happening here. So that's why we're not seeing that. If we load more, we can see here underscore block. Right here we can actually see there are no literals. Right, and that's because checksum equals false. If we go to our source file, we can see checksum equals false. Hasblock checksum, right, equals false, and then block gets copied because we don't need any literals at this point at all. Right, we have space block we can copy. So this sequence holds only a match operation, like a match copy. Right? And this is completely valid, of course. Sometimes we don't have literals at all. In fact, many of the later data blocks inside of an LC4 file will simply not have any literals because there's so much we can copy from previous sequences or from our output, right? And in fact, you can see here that there's so much repetition that we will see again and again. There are no literals. So if I click this a few more times, we can see here that max size yeah, hang on, I think I've maybe messed up the X traveling here a little bit, I suspect. Let's see if we can just fix that so I can get some nicer output here. The X pulse gets whenever there's a new line, we reset the X position to 0. And here we add 22 to it, which I'm not sure makes any sense, to be honest, but yeah. Yeah, we're gonna have to fix this, of course, at some point. At this point, we may actually want to sort of just skip this, trying to output this way, and instead simply say literals like this and match. We're giving up on the dream for now. It's fine. We will do something interesting later. So now if I open this file again, we are going to take a look at this. And here I kind of want to maybe fix this. It takes up a lot of space. We don't need that to be the case necessarily, right? But yeah, so here we can see our literals. And so if we go to our plaintext file, we can kind of match these together, right? So we read one sequence here, we have package, LC4 frames, test, and then we start on a match copy here, right? We match copy underscore frame, then we have literals again here, this one, and then the literals actually continue until the uppercase F here, right? Like this. And then we can copy rame here, right? And that's the match. And then we have a literal underscore descriptor, etc., etc., etc. We continue this until here. And then of course the compressor sees, hey, I can copy block, right, from here. That's the match here. And then we have underscore, block underscore is what it can copy, sorry. And then we have a literal checksum, right, because we haven't seen checksum before yet. And the match is equal false because we know we saw false here before, right? And so on and so forth, right? So the code that we have, in fact, here, the code that we have here is effectively the decompression code for an LC4 file or for LC4 data, right? And I said before that there was an edge case here, right? And of course the edge case, not of course, but there's an edge case here where offset can sometimes be less than match length. And when that is the case, we actually need to repeat characters some amount of time. And if I were to click, I think if that file that I was using now, if I were to click this enough times, let's test that hypothesis, we would actually run into this error. So I'm going to try that and we'll see. Okay, not quite. In this particular case, we have seen the entire file. You can see successful, etc. here. So we're actually not running into this case here. I can tell you that there is another file that I have definitely that would run into this. That is quite a bit larger, but we will see if we can actually show this here, right? So this is an Odin source file. You can see actually this is quite a bit larger, right? So it's 10K of data. We should run into this reasonably soon, to be honest. I said reasonably soon, it turns out maybe I was a little bit wrong, but I kind of feel like soon it has to be the case. We're only on, you know, we have 8.8K remaining at the moment, so I might actually quit this before that. I'm gonna try this a little bit. This is me clicking about as fast as I can. We are not hitting it, so let's give up on that. So I want to show you the actual kind of thing here. So we have copy start and copy end here, right? We have block dot something, right? So what we actually kind of want to do here is say if block dot offset is less than block dot match length, like this, right? We actually want to here repeat some characters, right? But it's not necessarily the case because block dot offset, right, will be less than match length if we are basically copying over the end of our output, right? Of our current copy index, right? So what we actually want to do here is we want to figure out which bytes we need to write until basically, let's say, the end of our thing, right? So that is represented essentially by saying copy bytes is equal to output, and then copy, actually let's say copy start is equal to copy index minus block offset Sure. And what we're gonna do here is copy end will actually be copy index like this, because that's what we currently have, right? We can't actually write, we can't copy beyond the copy index. That wouldn't make any sense, right? So what we're gonna do now in this particular case is we're gonna say that the copy bytes that we're gonna first copy are going to be copy start. And here, in reality, we could actually just do copy index here, like this, right? And remaining would be whatever, let's see, match length. Let's say that was 6. We had 2. I'm gonna say block match length minus len of copy bytes, like this, right? And now we have first a copy operation, right? So for our copy bytes, we want to actually copy into the, like this, right? And this mirrors exactly what we've done before. However, we also want to say for let's see, for ci in copy bytes, like this, output copy index no, hang on, let me just sort of think about this. We actually want to say no, this is not what we want here. For 0 dot dot remaining, like this, I in, we want to say I copy index plus I copy bytes I divided by len of copy bytes. So the operation here is going to be basically figure out how many remaining writes we have, and then loop through our copy bytes, right, modulo the len of the copy bytes, which means, for example, if we had 6 remaining but there were 2 bytes to write over and over, this means 0 would obviously copy the first of those, right? 1 would copy the second, right? But what would happen then is we would loop around, because we have a len of 2, right? So we have I is 3, right? Modulo 2, and so on and so forth, right? So we would be basically safe in this way. This should work. If nothing else, we can actually go to our LC4 file and say remaining here. And this, I can tell you, works just fine. I also have another version of this somewhere, sitting somewhere. No, okay, it's this one. Decompress. Let's see if we can find decompress : And of course, I should be clear here. We are 100% basically re-implementing parts of this code, right, in our GUI, right? So we're not using this as just a complete library and so on. So here you can see, if our offset is less than match length, we basically say, take the currently decompressed data, copy the copy bytes that we have, you know, so far, right? basically jump forward here and then say for every remaining byte that we have here, we want to go into this and say copy into the index +1 and so on, plus I rather, this. And so, yeah, that is what we have in this other code, right? It looks like it, at least. I think this logic should work fine. And this is basically a substitute for our other version, right? Let's remove that for now. And of course, here we actually want to also modify our copy index. Not there though. This should be len copy bytes, like this. And yeah, here we add the remaining ones. So we move forward in this, right? And this case remains exactly as it is. And that's it. Copy bytes here doesn't exist. We could just say copy bytes. And here we can actually say copy bytes equals like this. Should not be a problem. Now we have access to it in both. And so, yeah, I hope maybe that there was some, I hope this was informative in terms of how this works, to some degree at least. So just to go over this a little bit more again. When we read one of these sequences, right? This means basically we are reading this data block here, right? And the data block, as I said before, is this section here, compressed block format, right? We first read a token byte, right? And we saw this in data block read. We read this token byte here. The first 4 bits of that is literal length. And if we have a literal length of 15, we need to read more bytes for that literal length, right? That is the thing that determines how many bytes here can we read, right? So if we, let's say we had 16 literals, right? We would need to read first 15, and then we know that because we read 15, we need to read 1 additional byte. That byte will be 1, because then we have 15 plus 1 makes 16, right? If we had more, right, a lot more, we could have 15, and then we read 1 more byte, and 1 byte can contain 255. And in that case, we need to read even more. So we read even 1 more byte, right? And so on. So when we've read that, we know that we can read some amount of literals. In this particular case, we can read this amount here, right? This square bracket package up until test here, right? And then we move forward to a match copy operation, which is an offset, right? So this is how many bytes to go back in our current output, right? And we saw this in our source before, that we have this data block. We copy the block literals here, right? So now we've done that already. And then we basically say, hey, for this given offset, right? I want to, hang on, this needs to be there. And so for this given offset, I want to go back some amount, that's this here, right? And then copy from that start until start plus match length. Match length is a lot like literal length in that it uses token bytes, so it can be 15. If it's 15, we need to read more, and so on and so forth, right? And that number, we add that up, and we basically copy that amount of bytes from this copy start, right? Copy start was go back some offset amount backwards, right? And with that, we have what we need to copy, right? We write that to our output, right? And so that's now our copy output. So in this particular case, we read these literals, package LC4 frames, test, and then our matches underscore frame, right? And then we move forward, and so on and so forth. So we're gonna try to visualize this maybe in a clearer fashion. I'm gonna try to come up with some nicer way of doing this, because of course, when we actually have an episode that goes over this, that goes over specifically LZ4, this is not how we want to visualize it, right? And this episode, basically what we did was we read more and more data from this file. So we step through it like piece by piece, right? And so this we've done. We can now see that, okay, hey, we have this down. We can read this piece by piece. We can move forward in the file. This is not reflected here, unfortunately. But we're gonna stop there for now. And yeah, I'm gonna come up with a way to visualize this in a reasonable way in the next episode and so on. But yeah, okay, that's it for now. Have a nice day and ciao.